Today, we're navigating a circular track to find the sectors that get visited the most. The twist? The track is circular, and movements can wrap around. How do you efficiently determine the most popular sectors without simulating every single step? You're given the total number of sectors n and an array rounds indicating the start and end points of each round. A round means traveling from the current sector to the next in clockwise order. We need to return an array of all sectors that are visited the maximum number of times, sorted in ascending order. The challenge is handling the circularity and identifying the most frequent sectors. A straightforward approach would be to simulate every single step. We could declare an array to keep track of visit counts for each sector. Then, for each round, we iterate from the start to the end sector, incrementing counts, handling the wraparound explicitly. After all rounds, we find the maximum count and collect all sectors with that count. This works but can be inefficient if the number of rounds or the track length is very large, as we're explicitly traversing every single step of every round. This leads to a time complexity of roughly O, n plus m asterisk n, in the worst case, where m is round's length, and space complexity of big O of n. The key insight here is that only the first and last sectors in the rounds array truly matter. Consider this: any sector between rounds I and rounds I plus 1 will be visited exactly once during that specific subround. When we combine all these subrounds, the intermediate sectors within a continuous path from the absolute start to the absolute end will be visited. If the start sector is less than or equal to the end sector, we visit all sectors in that direct range. If the start is greater than the end, due to circularity, we visit from start to n, and then from 1 to end. All other sectors in between the rounds array are merely intermediate points that define the path. Effectively, we only care about the single path from the very first starting sector to the very last ending sector. We initialize a count array. If the start is less than or equal to the end, we simply increment counts for all sectors from start to end. If start is greater than end, we increment counts from start to n, and then from 1 to end. Finally, we find the maximum count and collect the corresponding sectors. Let's trace with n equals 4 and rounds are 1, 3, 1, 2. Our count array is initialized to all zeros. The actual start of the entire journey is 1, and the final end is 2. Since 1 is less than or equal to 2, we increment counts for sectors from 1 to 2. So, sector 1's count becomes 1, and sector 2's count becomes 1. The count array is now 1, 1, 0, 0. We then identify the maximum count, which is 1. Both sectors 1 and 2 have this maximum count. Therefore, our result will be 1 and 2. For our example, with n equals 4 and rounds 1, 3, 1, 2, the most visited sectors are 1 and 2. This is correct because the continuous path from the overall start, 1, to the overall end, 2, includes exactly these two sectors. You'll spot this pattern when dealing with circular arrays or tracks where the exact path doesn't matter as much as the overall start and end points. Also, when intermediate steps in a sequence can be abstracted away because their cumulative effect is captured by the boundary conditions. The time complexity is big O of n because we iterate through the sectors at most twice. The space complexity is big O of n for storing the visit counts. This interval trick is a powerful optimization for many circular track problems. Try the next problem involving circular arrays, same pattern. Don't forget to like and subscribe for more DSA insights.